So I could also ask a third question and ask you about any AI-enhanced app. And then I would probably see the hands of the majority of you. That is because we stepped into a phase when artificial intelligence is basically everywhere. And it seems that also everyone is an expert in it. And that is why I'm especially happy to see this many of you today, because I'm here to hopefully show you something new regarding machine learning. Namely, I'm here to present an idea that my team and I developed into a working solution. And just a small disclaimer here, I do not own the idea, but I had this great opportunity of heavily contributing to the whole project. So let us begin with a very short recap of how a typical machine learning project is usually conducted. You may come across a different set of phases here, but ultimately they are all pretty similar. We start with a problem that we need to thoroughly understand. A problem that we also think it might be beneficial to solve using some machine learning techniques. So we define it, and we plan some appropriate experiments. Once we've done that, we can start collecting our data. In this case, the more, the better, or at least to some reasonable extent. So once we have it, we begin to process it, and this is probably the most tedious part of the whole project. Data wrangling can actually eat up a lot of time, since we often have to deal with extracting features of interest, among many, many others present. We also often have to deal with the missing data. Sometimes we need to label the data. So it's definitely much more than simply dropping non-applicable entries like you would commonly find in some online tutorials. But if we manage to do this, we can proceed to probably the most exciting part of the whole project, which is model development. In this phase, we decide to use some kind of machine learning algorithm. We also choose our metrics to further evaluate our model with. We can then feed our model with the data that we collected, and we can also fine-tune it. Then we get some results, and hopefully we are satisfied with them. And the last phase is about utilizing the project and the whole model. And I marked this phase with a slightly different color on purpose. It is because not all projects end up with a deployment-ready solution. Some projects are strictly for research purposes, and others are simply not good enough. So there can be a lot of different things here. But the reason I'm going through this chart right now is because I would like to now lead you through our project, phase by phase, as it is defined here. We will therefore begin with the problem statement. So the problem we wanted to tackle was the assessment of the performance in mobile networks. These networks are changing incredibly fast. A typical mobile network is defined by thousands of parameters for each object within the network. And the state of such network is also additionally affected by some external factors, like, for example, the weather conditions, or temporary fluctuations in the location or number of users connected to this one network. So what we want to know is whether introducing some kind of change to the configuration of this network will result in any kind of change in the overall performance. So at the lowest level of complexity, our problem can be defined this way. We have a single network object, like a single cell. And we know that at a given moment of time, there was some configuration change, the moment that is here marked with a dashed line. So we have configuration 1 for the period before the change, and similarly we have configuration 2 for the period after the change. And now, how to tell whether any change in the overall performance occurred? And if it did, how to assess whether it was positive or negative? Well, there are some simple methods to do this. Usually a comparison before-after is used. So you take, for example, the average value of the KPI from the period before and a period after, and you compare them to actually say whether you note a gain in the performance, so an increase in the performance, or if you note loss, which is a decrease in the performance. And what is also more important is the term KPI. So I know that it is probably a very common term for the majority of you here, but it can also refer to all sorts of things, all sorts of measures. So in this case, I would like you to think of a KPI as of any type of signal that tells us what the current performance in the network is. Okay, but we have some solution, some simple method, right? But as you may imagine, this problem must be far too complex to simply compare the averages. And that is correct. And here's a good example. So on this plot, you can see the KPI values for a single cell in the network throughout more than 10 days of constant measurements. And although the title of the plot clearly tells you that no configuration change happened, you can see that we can actually quite arbitrarily choose some moment of division of this period and create these artificial before and after periods. And what we see here is that the average value of this KPI for these two periods is actually very much different. In this case, we have a decrease by more than 18%, and that is a lot. But why is that? Why does that happen? Well, because like I said, mobile networks conditions are often unstable. So in theory, we expect this KPI to be periodic, but there are many exceptions to this rule. What is more, such a KPI depends on dozens of other indicators. So the conclusion would be simple here. We just need a more sophisticated method. So what my team did is we kind of shifted the way of perceiving this problem. And instead of a typical approach, which is what is the current performance compared to the previous performance, we asked ourselves a slightly different question, which is what is the current performance compared to the expected performance? And by expected performance, I mean the performance that we would most likely observe in the network if the configuration change didn't really occur. So translating it visually, it would look like this. Instead of comparing the values of the KPI and the before and after period, what we want to do is we want to compare the actual measured values of the KPI and the period after to the KPI values that we would most likely observe if configuration didn't change. And we can achieve it by making some predictions for such a scenario. And I'm saying the keyword here, predictions, because this is exactly the moment where we will utilize a machine learning model. So on the left-hand side, the gain, so the increase in the performance, is given by the difference between the average value of the KPI from period before and from period after. However, on the right-hand side, the information about the gain will come from the difference between the predicted values of the KPI and actual measured values of this KPI. And this difference between the true values and the predictions is nothing else than just the error produced by the model. So now that we have understanding of the problem, and we also have an idea on how to solve it, a phase 2 of the project should come, which is data collection. But on this process, I will not elaborate very much, because we simply have not that much time. It is just sufficient to say, though, that we actually had tremendous amounts of data, and we actually spent a great deal of time extracting the proper features and proper input for our models, and on processing it for further modeling. And what I want to do now is to proceed straight to the experiment design. So we designed our experiment in this way. Knowing the moment of configuration change, which is once again marked with the dashed line, we took some part of the input data for the period before, and we used it for training. In this way, our model only learned the dependencies that held true for the configuration before the change. Then we used our trained model to make some predictions for the remaining part of the period before and for all the data from period after. Now, we took the model error for each measurement point from both of these periods, and we calculated the median error. So to calculate gain or loss, respectively, what we do is we subtract one median error from the other, and we divide it by the average value of the KPI in the period before the change, just to ensure that we get the result expressed as a percentage. And that's it. That's the whole idea. But I know it may seem complicated at first. Someone could even ask if we can actually believe that the model error will give us trustworthy information about the gain. Because after all, it's an error, right? Something that we don't want to have, or something that we want to have minimized. But let's consider together a simple example. Imagine that you participate in a survey, and you're supposed to give your estimates on how much would it take for you to complete some simple activities, like cooking dinner, doing laundry, paying bills, etc. Let's say that you provided your answers, and now you are supposed to actually perform those activities. And imagine that someone is going to measure the time that you actually need to complete them by talking to you on the phone and then checking the time of your call. A weird way of doing this, but the measurement would be valid, right? So the results of such survey might look like this. So what we observe here is actually a common fact. The fact that when we need to multitask or when we need to split our attention, we tend to perform worse. So in each case here, you underestimated the time that you needed, but only by some near constant value. So now for the sake of visualization, I will draw a line between those points. And I hope it starts looking familiar to you already. So if I were to inspect such a survey, I would say that you are totally credible. It's not like you said you needed 30 seconds to tie your shoes and then it took you 30 minutes, right? What I can see from this results is actually you are totally capable of predicting the time that you needed. You just didn't know that there were going to be some external factors, like a phone call, that were going to distract you. And this is something that we assume when working with our models. But to be able to make such assumptions, we need to be sure, and we need to verify actually, if we can really successfully model this particular KPI. And this is something that we did in our preliminary checks. So at first, we created a single model for each object and each configuration that were present in our data set. We checked the metrics, and this time we really wanted to minimize our model error. And we validated overall good model's performance. So we took the second step. And this time, we created a single model for all objects sharing the same configuration. And we, of course, repeated it for every configuration that we had. And this time, the ability of the model to accurately predict the values of the KPI was even better than for the single object models. So we took the third and final step, and we created a single model, this time much more complex, for all our objects and all our configurations from the dataset. And this time, the model performance was also more than satisfactory. Okay, so now I hope I managed to convince you that we can actually trust the error, that we can model this particular KPI, and that our experiments were well designed and our methodology was correct. So what about some results? Here's one example. So here we have two configurations, 3229 and 46795. We also have a moment of the configuration change, this time marked with red. We have the true KPI values, so the measured values, in black, along with the predictions, which are in blue. And we have just seen something very similar, haven't we? So the crucial information here, something that we know because we have our telco knowledge, is that for this particular change in the configuration, we can actually expect a decrease in the performance. And this is exactly what we observe here. Look at how the predictions in the after period are always slightly above the ground truth. So after the calculus, the change, so our loss in this case, would actually be around 16%. What is more, look how in the before period, the quality of the prediction is actually really good, like really high, because here, the model error is really minimal. And this is probably the perfect way of me showing you how our method works in practice. But now, let's just put those plots aside for a while. Do you know the differences and the similarities between a parrot and a machine learning algorithm? So just in case you don't know the meme, I have a very short summary for you here. And I admit, I did want to make you laugh with this one. But I have a valid point to make as well. Namely, I'd like to focus on this trait here. We know that models actually don't speak nonsense. A model can only respond to poor data. But it kind of refers to what I want to underline here, which is the fact that our solution has its limitations too. So first of all, the fact that our solution really works does not mean that we always get the perfect results. And except for trustworthy, valuable gain results, our method also sometimes produces nonsense. So to be as well prepared for that as really possible, we use some statistical tests to differentiate between statistically significant and insignificant gain results. But even these tests do not handle our uncertainty in 100% of the cases. And that is heavily connected to the second great difficulty, which is the lack of absolute reference. And by absolute reference, I mean some other assessments result that we know of that are objectively correct. So we can, and we of course do, compare the results from our method to some other methods, like for example the simple before-after comparison that I showed you before. But even those results are not to be trusted at all times. So because of all this uncertainty, we need to sometimes manually inspect our results and validate that they're actually correct. And to do so, we need to rely on some expert-level domain knowledge. And this, as you may imagine, makes the process of interpreting those results and drawing any valuable conclusions much longer. So I felt that this was the only decent and honest thing to do, to show you that our solution has also downsides, but so does any other. Because I dare say that for such complex problem and for such difficult and complex data that we have here, no solution can be ever perfect or totally universal. What is important, though, is that our method of assessing change in the performance by the model error works really fine, though. And what is also true is that there are some difficulties here, but it doesn't change the fact that our method is so good that it just stepped into the deployment phase, which is, as you may recall, the fourth and the last phase from our typical machine learning project lifecycle that I showed you at the beginning of my talk. And this is something. So to wrap this up together, I've showed you our idea. I've showed you that it works. And I've showed you that there are obviously some limitations to it. But what's in it for you, really? Well, I hope that after all, you were able to see something new, something fresh in machine learning. So my message here is not copy-pasted. Go use model error as a source of information in all of your projects now. No. What I would really like you to remember from my talk is that there really still is a place for something new, for some kind of novelty and innovation in machine learning. So as you have just seen, model error can be, in fact, turned into our asset. It's not something that we always have to just avoid or try to minimize. And what is more, if you plan your experiments correctly, and then validate the correctness of your approach at each and every step of your way, then you actually don't have to stick to rigidly defined principles. You can actually make them work for you. And the last thing, probably most important, I hope I was able to somewhat inspire you and to prove with my presentation that you can achieve great results, great outcomes by thinking outside of the box. Thank you.
Thank you very much, Marta, for a really interesting presentation. So now it's time for Q&A. So if you have any questions, then please raise your hands.
Hello, and thank you very much for nice presentation. I have a question on this prediction of the next availability of the KPI when we are talking about. Sorry. My question is that we can have two approaches. One is that we consider it as a prediction on its own. I mean, we have past values, then we predict the next value based on same KPI. Or the other approach is to, for example, find KPI 2, 3, or 4 which are related, which are correlated with this KPI, and calculate the next value based on those KPIs. So my question is that because both of approach have their downside and they have some advantages and disadvantages. So which approach did you take, and what are the benefits over the other approach? Because if I may add this explanation, that when some kind of changes happens, this is not just one KPI, like configuration change, not just one KPI that goes down or up. there are many other KPIs which are related and they are going ups and downs. So, for example, if you choose the second method, considering other KPIs, then you should consider also that those KPIs will be affected because of that configuration change.
Yes, so thank you for the question. A short answer, we use second option. So, but the longer answer would be that, well, we actually didn't really consider the first approach because that would, if I understand correctly, that would actually mean experiment based on some time series forecasting. And this is not the approach that we used. So we actually prepared the input. The input that was, that varied throughout our experiments, but it was consisted of some other KPIs, and that was it. So we did not actually pay attention this much to the time series of the KPI, just to the inputs, because actually this was the only reasonable way, when I think of it, to actually satisfy our requirements for the experiment, because we only wanted to take into account, when training the model, we actually wanted to only take into account the configuration before, so as to make sure that our model does not know the configuration after. So I guess that the first approach wouldn't really be applicable here even. So I hope that's okay.
Thank you.
Thank you. Any more questions? You see, like I told you, everyone is already an expert.
So hello, thank you for your presentation. I have one question about the methods. What kind of machine learning methods do you use for making prediction? As far as I remember, it is kind of regression utilized on time series. So maybe a few words about that.
Yes, but can I actually ask you something in return? Do you mean like the algorithms, like the choice of algorithm?
Yes.
Yes. So, well, it also yes, it was a regression problem. So that's correct. And as far as the algorithm goes, it was also it was changing, because I showed you the three stages of building some models. So for the smallest models, these that had only information about a single object and single configuration, then we also had limited and quite small data there, because there was only obviously one object. So in this case, usually, well, the simpler the better. So we often used simple linear regression. We also used some variations on it, like, for example, a ridge regressor. We also tested XGBoost, because it is proven that it works well with small data sets. But actually, as our experiments proceeded and as our models grew bigger, we actually could not use such simple models anymore. And finally, for this more the most complex model, we actually just used a neural network. So a deep learning approach.
How long does it take to train such a model? So you gather the data and you pass the data to the model, create a model, right? How long does it take?
So I'll just repeat in case not everybody heard. So the question is about the time that we needed to train our models. So once again, we created different models of different level of complexity. So those single models, for example, the ones that we use the linear regression for, they are actually like near instantaneous. So it's really, really fast. And as far as the more complex go, they actually required much more time, but we are talking about hours and not days. So it wasn't like that much time. Thank you. Yes.
Isn't this model, which is
Okay, well, that is actually a very important question. Well, everything that you said is really true. That's correct. So let me just quickly elaborate. So those three experiments that I showed you, they were mostly they were mostly for validating that we have good prediction capability. So we didn't care that much about calculating gain in this stage. We only wanted to verify that we can use actually those models, this approach, to calculate our gain, but later. So that was this preliminary check, and we only cared for the performance. And as I said, we only wanted, good performance. So we wanted to keep our model error at minimum, and so on. But in fact, later, as we proceeded to calculating gains, and we also did this for several models, we were also adjusting the amount of information that we treated as an input. So we were limiting the input, and we were, for example, cutting out those after configurations. So actually, our model did not have the knowledge or the input that considered those configurations after. So as not to, just like you said, so as not to disturb the idea behind the modeling. Yes, exactly. Thank you.
Are there any other questions? If so, please raise your hand.
Hello.
Hi.
How do you pick these first parameters to start research?
It's all mostly related to this telecommunications knowledge. So we have, like I said, there are dozens of other indicators, and they so the primary choice comes from the knowledge. Let's say that we know that some indicators are in relationship with the KPI that we actually wanted to model. So that was an obvious choice. And then there's this process of verification if those are actually the proper inputs. So there's like a whole procedure of checking it if we shouldn't append some other indicators to the list, and from that point it's kind of an iterative process. But it's mostly related to just the knowledge about the characteristics of the data.
Okay, thank you.
Thank you.
Okay, I see no questions, so thank you very much for a really nice discussion. Thank you once again, Marta.
Yeah, and if I just may say one last thing, those were actually all those questions that were totally brilliant, and I'm happy that I got them. So shout out to you. Thank you.